Okay, so at the end of the last class, we had two formulae that we wanted to use. Today. The first formula was for this eta function. Okay, so you remember we had that the partition function of a free boson. The partition function of a free boson was equal to 1 over mod eta tau, the whole thing, squared times eta times square root of im tau. Okay, from the fact that this free boson was modular invariant, obviously so. Okay, we deduced the modular transformation properties of this eta. Okay, and you remember we found. Now I'm reading it out from this textbook. Somebody has their notes; they can confirm. We found something. We found eta. So we found that eta of I, let's say t. Okay. At large tau went like let's see, eta of it went like square root t times e to the power pi by 12t. Right? Yeah, so that looks good. Okay, when t is this t was inverse temperature. So t being small was temperature being large. Okay, so this grew like e to the power pi by 12 temperature. You remember we had this this way of understanding it from extensivity. Okay, we found this. Now this was one result that we're going to use in 2 minutes. The other thing we found also in the last class was we derived this Cardy formula. Okay, you remember we used modular invariance of the partition function to replace the high temperature, to estimate the high temperature behavior from the low temperature behavior. Now low temperature behavior was very easily estimated because low temperature behavior was dominated by the vacuum, by the energy of the vacuum. Okay, this was this minus c by 24. And again, I'm going to read it off from this book. I hope they've got it right. Anyway, you have your notes. This went like z of t went like, again when t is very small, so high temperature, went like e to the power minus 4 pi by t, and then, so I'll write with a plus here, c by 24. Okay, we had this behavior for the high temperature behavior of any unitary conformal field theory. Where did we use unitarity? We used unitarity in the following place. We assumed that the energy, the lowest energy state in the theory was the state corresponding to the identity operator. That was true in unitary theories, not necessarily true in non-unitary theories. Okay, so that's why we used unitarity. If we wanted a more general formula, we could change this. C by 24 to C by 24 minus H. You know, this C by 20. We had the vacuum energy being minus C by 24. The vacuum energy on the left moving side was minus C by 24. But suppose the lowest energy state operator was not an operator of dimension 0, but of dimension h min. Then instead of getting lowest energy being c by 24, minus c by 24, we would get h min minus c by 24. Okay, so this c by 24 is replaced by c by 24 minus h min will do the job. Okay. Not that we're going to use this very much, but just so that you know that there is a more general formula that applies to non-unitary theories. Is this clear? Okay, but for now, let's forget this H-min and just work with the unitary formula. Notice that every theory always has the identity operator in it. Okay, so H-min cannot be cannot be greater than 0. So H-min is always always a negative number or 0. And so it's always true that the growth in any theory, unitary or not, it's always true that the growth is at least as fast as zeta t is equal to e to the power 4 pi by t into c by 24. That is always true. Okay? Fine. So now I wanted to put these two things together. We started doing this in the last class. Yes?
So in non-unitary theory, is it necessary that h mu will always be less than 0?
No, no. Can be 0, can be positive. I mean, there are no guarantees. I mean, if h is less than 0, the theory is actually in the minimal models we always have, except for p is equal to p prime is equal to p minus 1, there's always an operator of negative dimensions. But this was not a logical necessity. Right? You could have had some theory that was non-unitary without having negative dimensions. In minimal models, it never happens. But just logically, it's not clear to me that follows. Okay, excellent. Other questions or comments? Perfect. Okay, so now let us study a theory which has a finite number of primaries. Okay? We don't really care what these primaries are, but the number of primaries must be finite. Okay. Now, our primaries might have null states or not. But if they have null states, that only reduces their growth. Okay? So, the growth of states of any one of the modules built out of a primary, any one of those modules is always, so growth is always faster than. Now, when I say, okay, let me write the statement then. It's always faster than what you would get from 1 over mod eta square. Why is that? Why is that? You see, sorry, it's always slower than. Why is that? Because if there were no null states in the problem, okay, if there were no null states in the problem, then each module would generate a mod eta squared, an eta from left movers and an eta from right movers. Why does it do that? Because you get the whole module by acting in an unrestrained manner by L minus 1, L minus 2, and so on. That generates these eta and eta bar. Okay? Now there might be null states, in which case this will grow slower. Now, this thing starts with some particular dimension, but at very high temperatures, that doesn't matter. Right? That's just some overall prefactor which doesn't matter in estimating the dimension. Okay, so this is a good estimate for a lower bound, upper bound. Growth is always less than upper bound. Oh, the upper bound on the growth of each module. Now, this theory has been assumed to have a finite number of modules. Okay? So then there will be some number, which is the number of primary operators, some finite number. And once we put that number, this gives us, tells us that the growth of states of the minimal model cannot be faster than this. This clear? On the other hand, we've got the other kind of inequality here. We've got, so this is from finite number of primaries. If it was not a finite number of primaries, then the number of primaries can grow with energy. Okay? And that could raise the amount of growth. This is not just a hypothetical thing. In every C greater than 1 model, it happens. Okay? In C greater than 1 models, the number of primaries, the growth in number of primaries with energy of the primary is faster than the growth in number of descendants with descendant level of the descendant. If that happens, then the growth of descendants from one primary is not a good estimate for the total number of states. It's dominated by how fast the number of primaries grow. But if your number of primaries is finite, that cannot happen. Because there's a maximum energy up to which you do it. You go to much higher temperatures than that, all these energies are like zero.
But you can have finite number of primaries even in a energy in some finite scale, right?
Didn't understand. What do you mean finite scale?
I mean, you can have continuum of primaries some range. H goes from let's say 0 to 1.
Yes?
You can have infinite of them, infinite number of primaries. Can it not have?
Some theories have that, but minimal models don't, because they have only a finite number of primaries.
Okay,
So the assumption for finite, in fact, most theories will have what you're saying. Yeah, or maybe not an infinite, but will have, as you increase your range, that will go to infinity. A theory with a gap, not a continuum, will have finite number in any range, but that finite number will grow with energy, often very rapidly. Most theories are of that sort. But the whole point of these minimal models is they're not of that sort, right?
So
they have
I'm interested in minimal models.
yeah, that finite number of primaries was to focus our attention to minimal models.
I think you just want to say independent of temperature rather than finite.
Independent of scaling dimension, you're saying. Really, all I want to say is that the growth in primaries is not faster than the growth of states in a descendant. Okay? So we've got a certain estimate for how descendants grow in a primary, right? E to the power square root e with some number. As long as the growth in primaries is not faster than that, everything I'm saying will follow. Okay? But in particular, minimal models, it's certainly true because they're finite. Okay? So good point. Okay. Other questions or comments? Excellent. So this growth is less than equal to this. Now, you know, when I say less than equal to, you have to understand it right? I'm writing a partition function. What you really want to do is to, from that partition function, extract number of states as a function of energy, and that number should be less than equal to. But because these behaviors are very simple, because we're just looking at leading large temperature behavior, it's a one-to-one map. If you've got a particular scaling with 1 over t, that number, the same number will come in the growth of density of states, and if that number is larger, the growth in density of states as a function of energy will be larger. So I'm not going through if I was a mathematician, I would be more careful about what I'm saying. But we all understand each other, right? Okay. Excellent. Excellent. So there we are. We've got one inequality. But we've got the second inequality, which was growth is greater than equal to e to the power 4 pi by t into c by 24. That's clear. That's what we derived from Locality formula. Okay. Now this eta is like mod squared. So the thing that we got, this was like 1 over eta, sorry. Will be multiplied, which, this growth? Yeah. This growth, it's true. I mean, it has some undetermined prefactor. Okay? Cardi formula really gives it to you with, no, actually, Cardi formula would give it to you with prefactor 1, if it had a gap. Because you see, all we did was take the vacuum energy and modular transforms. No number of primaries. No number of primaries. That's important. Right? Because in the theory with the gap, like minimal models, this is correct with correct coefficient and then exponentially suppressed. Okay, excellent. Excellent. Okay? Now, how can both of these be true? Okay? Okay, let's estimate this growth. This growth was the square root t. I'm not writing, it won't matter, but maybe at a later point it'll matter, but right now, this is like e to the power, what is it? That goes like e to the power pi by 60. Right, because you mod squared the eta growth. Okay? Now, 4 by 24, that's also a 6. So that's sort of nice. Since the growth has to be faster than this, Okay, so we've got, you know, our growth has to be faster than, let's say we call this alpha. The growth has to be faster than alpha, but growth has to be slower than beta. A solution to these double things exists only if beta is larger than alpha. So that you can be faster than alpha but slower than beta. Okay? And so it must be that beta, which was pi by 6, is greater than, okay, is greater than c pi by 6. And therefore, c must be less than 1. It's not that we didn't know this fact. We started our analysis of minimal models last class by very simply deriving this fact. Okay? But it's sort of nice that it comes out of simple analysis of modularity. Is this clear? Any questions or comments about this? Excellent. Excellent. Now, let us suppose that now I want to deduce one more thing. Well, firstly, I don't know if you remember, but you remember the structure of null states of primaries in these minimal models? You remember every primary had 2 null states. Okay? There were the RS and then P minus R, P prime minus S. Okay? Each of those gave rise to their own primaries. And then each of them had 2 null states, but these 2 null states happen to be equal to each other. So the next stage we once again got two primaries. And then each of them had 2 null states, but these null states happen to be equal to each other, and so on. You remember we derived the structure of states of characters of a minimal model in the last class, in the last semester. Okay? Notice in particular that this is an infinite sequence. It's an infinite sequence, and so could result in a significant cut down in the growth of states. In a way, no finite sequence could do. If I had a finite sequence, on the other hand, what I would get at low temperature is some polynomial correction to the same growth that we would have got from eta. Okay? Why is that? Okay? What we would have got is, like, let's say the multiplying the growth of eta. See, suppose you had a finite number of null states. Then we would have got eta times the bare growth of the primary minus eta times the bare growth of the first primary null state. Then maybe some other plus. So some number of plus minuses all multiplying eta. Is this clear? So this number of plus minuses would have been of the form, this would have been eta of the h of the primary, maybe then by t minus h prime of the first descendant, some finite number of these. Sorry, times t, because t is just the length of this thing. Okay? Now, sorry, that was important, not by t. Yes?
Just a question from the previous thing. If this alpha and beta are the same, can we say that your number of null states, there is no null state in nullity when C is equal to
if it happens that alpha and beta are the same, okay, then, you know, this is a very delicate situation. You have to keep track of power law prefactors. Can we say, okay, let me first address the question. Can it be that alpha is exactly beta? Can it be that alpha is exactly beta in the sense of these coefficients? in the case of c equals 1. Yeah. And could that have been consistent with a finite number of primaries? That's what you're asking. I think it could not have. Okay? Let's try to make that argument. Okay. For that argument, we have to be a little more sophisticated. For that argument, we have to look at not just these exponential growths, but also this power law. Okay? This power law at small t is a small number. Oh, but that is doing it. Yeah, beta was, which one? Beta was in what we drew. Yeah, beta is this guy, right? This guy. Yeah, okay, so maybe it could have been. Maybe I said it wrong. Because we have this power law correction in the growth of any one module, that would have made alpha less than beta. You see, because it's e to the power something times a small number. Square root, 1 by square root t. I hope I got the square root t right. But, okay, and let me be more cautious. The power laws will decide whether that could work or not. Okay, because the power laws will give you now, because the exponentials will tell you that the two things are equal. Now you would have to look at the first correction to that. We control the first correction in both cases. The first correction comes with coefficient 1 from Carnot formula, and comes with something very specific from the zeta. Okay, so you would analyze that. If I've written that power correctly, let me check that carefully. If I've written that power correctly, 1 over root t, 1 over root t, okay, then it cannot work. You see, because now this guy is not bigger than this guy. Because t is small, so 1 over root t is bigger than 1. So if the exponentials match, this inequality is still violated.
So that would not explain the finite number of primaries at c equal to 1.
C equals 1 does not have a finite. That would explain the fact that C does not. That would be one explanation of the fact that C does not have a finite number of primaries. Though I hope this 1 over root t is right. You're sure? Excellent. Then we're sure. Okay. Okay, excellent question. Other questions or comments? Okay, but all we're doing is just looking at this inequality. The case where the two exponentials are the same, just go to the first next subleading order. Okay? Great. Now, coming back to this, suppose we had a finite number of primaries. We would get something like this. Then what we would do is Taylor expand each of these terms. Perhaps the ones would all cancel, and we would get some t to the power. But if you have n number of these things, at most you'll get some t to the power n. So we'll get some polynomial correction of this exponential growth. Okay? So if we have a finite number of null states, if our modules are such that they have a finite number of null states, then the estimate we made for the growth of each module up to power law corrections is not just an upper bound, it's a true estimate. We're not correctly estimating the power law corrections, but the exponential is correctly being estimated. Okay? And now, then we have an accurate estimate of this. But now suppose C is strictly less than 1. I mean, it's not equal to 1. It's a minimal model. C is less than 1. Then we have, okay, suppose C is less than 1, and for instance, we're dealing with a unitary theory. So that this estimate is not just upper bound, it's a true estimate. Okay? In that case, now you see we violate there's the other problem. Because the correct estimate of growth from estimating eta is too large compared to the Cardi growth. Because we've got an estimate from the Cardi growth, which is an exponential that's smaller than the growth from eta. Okay? So there's a version of this argument you can give for the non-unitary minimal models, but let's stick with this because it's the same kind of argument. Okay? And so we argue that the only way modular invariance can work is if each module has an infinite number of primaries. In that case, the effective growth of states for each of these modules, okay, might be well smaller than the growth of eta. And that is indeed the case. You know, we will come to this as we go on in our studies. But there is this notion of quantum dimension of a module, okay, which is basically the coefficient in the growth. All modules grow like e to the power something by t. The coefficient in that growth is called the quantum dimension of this module. And one can show, and we will get to this at some point, that these quantum dimensions of all these operators, this quantum growth rates, are always less than 1. So that they always grow slower than the eta function grows. Okay? Because of all these null states. Okay? And that's what makes it possible for modular invariance to be maintained consistent with the Cardi formula in these minimum ones. Is this clear?
But these constants are like not function of t. They are some constraints.
Yeah. What they really are constraint. You know, what we're doing is getting inequalities in the number of states as a function of energy. T is just a convenient way of encoding that. Okay? You know, you see that you can go between these partition functions and the number of states, right? Just by thermodynamics. It's a one-to-one, simple, monotonic thing. So that's all that matters. Okay? Is this clear? Excellent. So we've already, by doing some very minimal exercises, you know, we hardly had to write anything down. We've seen that there's some tension between unitarity and minimal models, and that it could only work first if C is less than 1, and second if all modules have infinite number of primary operators. Okay. Now, what we're going to try to do is get more quantitative. What we're going to try to do is to actually understand how every particular module transforms under modular transformation. What do I mean? Okay. Suppose I've got this torus. I've got this torus and I compute the partition function on the torus. There is always one way of looking at the partition function by cutting it and making this our space. So that's a line of constant time. Okay? If I cut it like that, then there is a Hilbert space way. There is a Hilbert space way of computing this torus partition function. The torus partition function is simply given as follows. As we have seen, representation theory organizes operators or states. Same thing by the state operator map. Operators or states into modules. The lowest operator in that module is the primary, and then there are the descendants on top of it. Okay? And as we have seen, these minimal models have a finite number of primaries. So, let us give some labeling to these finite number of primaries. Let me remind you of the labeling. We discussed this labeling when we discussed minimal models. Let me remind you. Minimal models are characterized by two integers, p and p prime. We're not restricting to unitarity now. Had we been, that would have been just one p. P prime would have been p minus 1. So we make the convention p prime is less than p. Okay? These are the labels for the models. And then the operators in each model were characterized by two numbers r and s, such that r was less than p, and I'll check if that was p minus 1, I can't remember. Maybe minus 1. Let me check. Yeah, less than equal to. Okay, so it was correct. Okay, so the primaries that occur in minimal models, the minimal models themselves are labeled by two integers p and p prime relatively prime. And then the primaries that occur in these minimal models are labeled by two further integers, r and s. Okay, just let me remind you of one or two other things since we started talking about this. Through this lecture, I will sometimes use the notation 2p prime is n. Okay? And 2pp prime is n, and the inequivalent were these guys, and there was one more inequality. P prime s is less than pr, right? One of these symmetry transformations told us that we could restrict attention to p prime s is less than pr. Okay. So we'll be doing it more accurately as we go on. But very roughly, ignoring factors of 1, imagine p and p prime are large. Okay? Imagine p and p prime are large. The total number of integers here would have been p times p prime, okay, which was n by 2. And then this additional constraint, which is basically one side is less than the other, would give you sort of like n by 4. I'll give you more accurate estimates as we go on. Okay? But sort of like n by 4 distinct primaries. This is more or less right when p and p prime are both large. Okay? Anyway. So what we do, this torus partition function then must take the form chi rs. Okay? Chi bar r prime, or let's call it r bar s bar. Okay, times some matrix m, or some quantity r s r bar s bar, where every element of this m, every m r s r bar s bar is a positive integer. Because what we are saying is that the state content of our theory has, let's say, 3 copies of left moving rs and right moving r bar s bar. Maybe 4 copies of left moving r plus 1, you know, rs is equal to 3, 4, r bar s bar is equal to 9, 20, whatever. They have to be relatively prime. But that m just tells you how many copies of operators we have with these left moving and these right moving dimensions. Clearly the number of operators is an integer, or the number of states, number of primaries is an integer. So we've got this structure which determines the torus partition functions. Okay? We sometimes write this in the following form: chi bar m chi, where we understand that this runs over all labels for holomorphic operators, this runs over all labels for anti-holomorphic operators, and this is like a matrix whose left index is anti-holomorphic and whose right index is holomorphic. Clear? Okay? So z of tau must take this form. M is some given matrix of integers. Okay? Z of tau is of this form. M is a given matrix of integers. What about these chi's? Well, the great thing about chi's is that they're completely known, because they're completely determined by symmetry, and in particular, had there been no null states, they would have been 1 over eta times dimension of primary. But now we've got a few null states, but we know the structure of null states. So each null state gives us, 1 over eta minus 1 over eta times dimension, blah, blah, blah. So it's just some sum gives us the answer. Okay? And if you go back to the structure of null states you worked out, you'd easily figure out what the formula for chi of eta was. I'll be writing down in a minute. Okay?
What do these elements of M tell us?
The number of operators with those dimensions.
With RS in the
Left and yes. So suppose you had an operator whose left moving content was HRS and right moving content was HR prime S prime, R bar S bar. The number of operators of that form is n. Okay, clear? Okay, so this torus partition function seen by cutting this way is clearly this, because this was the left moving trace over the module. This was the right moving trace over the module. What way? Okay? And then we just sum. So it's a very simple thing. From Hamiltonian point of view, clearly the partition function must take this form. Is this point clear? Okay? However, one could equally have worked it out by cutting like that. Okay? And one would have got the same thing, but with all chi's replaced by chi of minus 1 by tau. Because that would have been quantizing by thinking of that as time. And that makes the transformation tau goes to minus 1 by tau, just that, as we've discussed, right? And so, this structure, and of course we could have done by quantizing like this, diagonally. And that would have made the transformation tau goes to tau plus 1. So what we understand from this is that consistency demands that this quantity, of course, is modular invariant. We know that. This quantity should be modular invariant. Okay. But the new element here is that, let's say I'm doing tau goes to minus 1 by tau. Okay? I've got a new expression of this form at the level of characters. It's also true that z of tau, z of minus 1 by tau, but that's same as z of tau. So let me write that. Z of tau, which is equal to z of minus 1 by tau, is equal to chi bar of minus 1 by tau, m chi of minus 1 by tau. Okay? But originally z of tau was chi bar of tau, m chi of tau. So these two things must be equal to each other. But chi and chi bar for given primaries are known. So one can figure out what happens when one computes chi of minus 1 by tau for any given primary. Okay. Now, since every left moving part of the partition function can be written as some linear combination of chi of taus for allowed dimensions of minimal models. Okay, but can also be written as, since that is the case, it must be true that each of these guys is some linear combination of chi of taus. Okay, this guy with one set of labels, let's say Rs, could be a linear combination of chi of tau with all labels. R prime, S prime, R prime, S prime summed over all allowed values. Okay? But this must be true, and we will check in a minute that it is using formula. Okay? So, people in conformal field theory very confusingly use this terminology. Let me say what it is in the map. You say, well, let's write the equation m of minus 1 by tau is equal to S times m of tau. Now this is again a matrix equation. It's a different kind of matrix from, let's not call this, this was chi. Chi of 1 by tau, minus 1 by tau is equal to S times chi of tau. This is again a matrix equation because each of these chi's carries a label. So if I put a label here, I'll get an alpha, beta, and a beta label here. And beta summed over. So it's a matrix equation. Different kind of matrix from M because it has two holomorphic indices. Okay? And anti-holomorphic characters are just complex conjugates. Okay? Anti-holomorphic characters are just complex conjugates. So we get chi bar alpha minus 1 by tau bar is equal to S star alpha beta chi beta. We have to figure out what this S is, but let's suppose we found it somehow. This matrix, by the way, is called S, and it's very confusingly called an S matrix. It's extremely confusing. I remember as a student I used to find, I didn't know this stuff, but I'd heard that conformal field theories have an S matrix, but I also knew that conformal field theories don't have an S matrix, and I found it extremely confusing. Okay, I suppose it comes from the not very well-known fact that the number of letters in the English alphabet is finite. Okay. Nothing to do with scattering, okay? Nothing to do at all with scattering.
What does S stand for?
It stands for S transformation. Tau goes to minus 1 by tau. That modular transformation is often called an S transformation. Same S when we say S duality in quantum field theory. That S. That has nothing to do with S matrices, but that's this kind of S. Okay?
For the non-compact, you will just identity. Because the character is just the beta function.
For the non-compact case, yeah. Now, you have to do this character by character. And the characters are labeled by each of the momentum modes. Okay? So you will have to do that transformation as well. Okay? So it's a bit more than that. Okay. In fact, a lattice example of we maybe come to that. Yes, please go.
How does this transformation change M, like in terms of number?
Excellent. So Rajat's asking exactly the right question. We had Z was equal to chi bar M chi. Now, under an S transformation, okay, chi changes to S chi. Chi bar changed to S star, but now that's acting from the left. So it becomes S dagger. Okay? So Z goes to chi bar, S dagger, M, S chi. But it has to be the same. Z goes to minus 1 by tau. Can't give us something different. So it must be that M is equal to S dagger MS. Okay? It must be that the M matrix sometimes called pairing matrix, because it pairs left and right, or at least I sometimes call it pairing matrix. I don't know if anyone else does. Okay, it's a good name. Okay, it pairs left and right together. This M matrix is invariant under unitary transformation, this S dagger type of transformation. S dagger MS is equal to S. Okay? The statement of unitarity, once we work in terms of modular invariance, once we work in terms of characters, becomes the statement for the S transformation. Now, similar statement for T transformation. There is some T matrix, we'll compute it momentarily. Okay? But there is some T matrix which implements these T transformations. Tau goes to tau plus 1. And it must be that T dagger MT is equal to M. Okay? These are necessary and sufficient conditions for modular invariance.
This also, you don't have to impose locality on top of this.
You're asking whether this guarantees locality? Okay, there is the following theorem. The theorem says that if this is obeyed, and a similar condition is obeyed for 1-point functions in the torus. We're looking at 0-point functions of the torus. Okay? Then every other condition, including your locality constraints, are obeyed. So almost. In 2D conformal field theories, the theorem tells you that every condition you want is obeyed for a field theory on arbitrary genus. You take this theory and put it on an arbitrary genus manifold. Every property you want on that arbitrary genus manifold is obeyed. It's a magnificent theorem.
So this condition and
A similar condition for 1-point functions on the torus.
And that is sufficient to
Guarantee everything. The basic idea is that you take a genus 2 surface and you got make a very long tube. You can replace it by OP on the torus. Okay, that's the basic idea. Okay, so this Frieda and Schenker, various such people proved these things, and it's very powerful because it's a complete set of conditions. If these are obeyed, the theory is good. You don't have to worry more. We don't have that complete set of conditions in 4 dimensions. In 4 dimensions, all we have is this lowbrow associativity of the operator product expansion, crossing symmetry. And we know in 2 dimensions that that's not enough. We just know that. Okay? You can make examples where that is obeyed, but not these more complete conditions. So it certainly seems to be the case that that will be true also in 4 dimensions. In fact, I think I can probably give you an example where I strongly believe that's the case. But we don't know what the additional condition is that that replaces this. And the big difference is that what we were discussing last time, namely that space and time and finite temperature are just different objects in higher than 2 dimensions. Because space and time were the same in 2 dimensions, both circles. That allowed real power. That difference is somehow very confusing. And people have tried working on Torus, nothing works. I don't know of any claim for a complete set of conditions that you have to check in higher dimensions. So amazing, right? With 2004, and our level of ignorance about conformal field theories is this high. We don't even know what the complete set. We know some necessary conditions. It's crossing of operators, but we don't have sufficient conditions for behavedness of conformal field theories. I find that amazing. For instance, let me give you one example where I think it will certainly go wrong. Suppose you take a theory with a global symmetry, and by fiat you restrict attention to those operators that are invariant under that symmetry. Okay. Take ON vector model 2 plus 1 dimensions. This ON version of Wilson-Fisher theory. And by fiat, restrict attention to only those operators, okay, which are ON invariant. Nothing will go wrong in operators, because if you restrict to ON invariance, operator product of two things that are ON invariant will give you something ON invariant. Operator algebra will close. Every condition that the bootstrap people impose will be met in the sector. Yet it seems extremely unlikely to me that this is a good theory. Because you see, the way we know how to restrict attention to things that obey a certain symmetry is by gauging. And precisely, that does it in a local way. And precisely this gauging process in 1 plus 1 dimensions produces twisted sector states. Do you remember from our discussion of orbifolds? You can try to restrict attention to those operators that obey invariance under a certain symmetry, x goes to minus x. That will not give you a well-defined 1 plus 1 dimension field. It will if you also add the twisted sectors. And indeed, in 2 plus 1 dimensions, we know of a way to actually restrict attention to singlets under, let's say, ON or SUN. That is coupled to a Chern-Simons gauge theory. Chern-Simons coupled gauge theory, and take k goes to infinity. But we know when we do that when we compute the partition function of the theory on a torus, we get, in addition to the contribution from these matter fields, the contribution from the Chern-Simons gauge field. I said take k goes to infinity because that then makes the coupling between the Chern-Simons gauge fields and the matter fields 0. But that changes the partition function. So we know the right way to do it. That will be correct. This must somehow be wrong. What goes wrong? How do you see if I just do this, that's wrong? I don't think anyone's clearly answered. I'm not aware of it. Okay? So, you should never underestimate our level of ignorance about extremely basic things. Even, in a sophisticated age, the level of ignorance is vast. What we know is such a small amount of what there is now. Yeah.
So in the case of ON vector model, what were you pointing out? That if you look at the...
Okay. Take the ON vector model. Restrict attention to those operators that are singlets under ON. Yes. Okay? They have a nice OP, so every condition you impose from the bootstrap is correct. Yes. So I wanted to make two arguments. I'm deeply suspicious that this will define a consistent quantum field theory. Meaning one that you can put in an arbitrary genus manifold, for instance, or arbitrary space, for instance, that consistent in have all the properties you want. Let me give you two arguments. The first argument is by analogy. Had we done such a thing in 1 plus 1 dimensions, it's like doing an orbifold. Restricting attention to only these operators is like just cutting down the spectrum of operators. But we know that consistency demands we also include the twisted sector states. And that is analogy. Now you may think, okay, analogies are good, but maybe it's not a correct analogy. Now I wanted to give you, second part was to give you an argument that works directly in 2 plus 1 dimensions. Saying, look, when you try to restrict attention to some sector, is there a way that we're familiar with in physics. We know will make sense because we've had 50 years of experience with this, 70 years, that will give you a well-defined theory. One way is to do gauging. Okay. Now, gauging of discrete symmetries. Okay, here this was continuous, but gauging of discrete symmetries in 1 plus 1 dimensions was very nice because it could be done without the introduction of a gauge field. Now we're looking at a continuous symmetry in 2 plus 1 dimensions. So gauging will require you to put a gauge field. Now, were we in 3 plus 1 dimensions, we would be sunk because the gauge field would have its own dynamics, and gauging, if you try to use this approach, would completely change the theory, would completely change the spectrum of operators. Okay, that would be one way of doing it, but that would be nowhere near to what you started out trying to do, namely just restricting attention to the ON and varied operators. In 2 plus 1 dimensions, you're on better ground because there is a way to gauge without introducing new gauge invariant local operators. And that is gauging with a gauge field that is coupled in a Chern-Simons way. The great thing about a Chern-Simons self-coupling in 2 plus 1 dimensions is that the kinetic term of the gauge field is such that there are no propagating gauge bosons, which means there are no new local operators in the theory. However, even though there are no new local operators, there are new global degrees of freedom. Okay, so what I wanted to point out was that any way I can think of restricting attention to these things introduces new degrees of freedom. That's what I wanted to say. This makes me suspect that it's not consistent even in 2 plus 1 dimensions. Just restrict attention to. Well, I think almost anyone who's thought about this problem will agree with me. But I don't think anyone will say it's not consistent because you have violated this necessary criterion that every theory that should obey. I don't know of one, at least. Was that clear? Yeah. Okay. Excellent. Okay. Now, so this M matrix that we were discussing has to be invariant under these unitary, these transformations, these S transformation and the T transformation. Let's first discuss T transformations. Okay, I'm going to have to stop class 10 minutes early today because Narayan's here. Let's see how much we can do. Yeah. Okay. Let's first discuss T transformations. Can we figure out how the module chi transforms under T? T on chi is equal to what? S is equal to what? Please.
So in C equals 1, T equals 1 case, we didn't have to check whether, we didn't have to see what the one-point functions of the operators were. In case the modularity variance on for 0-point functions was sufficient.
Yeah, that's because we had a Lagrangian them. You know, we had a Lagrangian, we knew what, if I want to compute the partition function on genus 12 surface, I know what I do. I compute that path integral. Again, we're talking about something more abstract. You don't have a Lagrangian, you're just specifying correlation functions. Yeah, but it's an excellent question. It's an excellent question, but we know beforehand that the boson is well defined, right? You can lattice it and compute it, right? There's no issue. That's a more physicsy way of knowing than this abstract stuff. Okay, excellent. Please go on.
It seems like this these transformations act on these characters, but is there a way that they act on the Hilbert space?
Transformation.
Yes. Because that character is for some primary.
Yeah, no, I don't think it acts like on a state, for instance. This is an action on a partition function. Yeah, think of it like that. Okay, other questions or comments? Okay, excellent. So now let's look at the action of T on this chi RS. Okay? What does T do? It takes tau goes to tau plus 1. So you might at first think it acts in a complicated way, But of course not. Because remember that q was e to the power 2 pi I tau. And so q to any integer power is invariant under tau goes to tau plus 1. But let's imagine a module built out of a primary. That primary has some weight h, some scaling dimension h. So its character is q to the power h, then some number of descendants at level 1. In fact, at level 1 it will be one descendant. But okay, I won't specify. Plus q to the power h plus 1, plus q to the power h plus 2, some other number of primaries and so on. Now I'll write this as q to the power h into 1 plus q number times q plus number times q squared plus and so on. Now under tau goes to tau plus 1, all terms here are invariant. This term transforms. It transforms like q to the power h goes to e to the power 2 pi I h times q to the power h. And so we see the whole module picks up under a tau goes to tau plus 1, picks up a given phase. The phase is completely determined by the dimension of the holomorphic dimension of the operator. Okay? So suppose now we're looking at, so what we've got is chi alpha goes to q to the power e to the power 2 pi I h alpha times chi alpha under modular transformation. Okay? So now how is this bilinear of chi and chi bar, how is this bilinear of chi and chi bar going to be invariant under tau goes to tau plus 1? Clearly, only if every non-zero term that appears, so there's a term that couples some primary, left-moving primary with some other right-moving primary, it will be invariant if and only if all non-zero terms that are coupled have h minus h bar equals to n pi. So if you couple alpha with beta, it must be h alpha minus h bar beta is 2n pi. Why is this? Because remember, chi bar transforms like complex conjugate. So it picks up the minus phase. So we get e to the power 2 pi I h alpha from chi, but e to the power minus 2 pi I h bar alpha, h bar beta for chi beta. But the bilinear has to be invariant, and so this must be true. Okay? And so we realize something very simple from T invariance. The couplings, the bilinear couplings between characters and complex conjugates of characters have to be of a form that they couple only those characters and those complex conjugate characters such that h minus h bar differ by a negative sign. Now, okay, it sounds very beautiful, but of course we always knew this, right? This was simply the statement that we're on a torus. So momentum must be n by r, r is 1. Momentum must be n, h minus h bar was n. So there's no surprise, but it comes about in this more fancy way. It's all the same thing. No surprise. So this was no surprise. Okay? But we see that from this more abstract way, the coupling between character and anti-character has to be such that the dimensions of operators, whole dimension and of the two operators differ by an integer. This is clear? Okay. This is a condition that's really easy to fulfill. One way to fulfill it, though not the only way, but one way to fulfill it is couple only an operator on the left with its complex conjugate on the right. This is called a diagonal invariant. You couple h alpha with h bar alpha. Then h alpha and h bar alpha are the same. So h alpha minus h bar beta is h alpha minus h alpha, which is 0. So this condition is obeyed. May not be the only way. In general, it's not the only way. But this would be one way of satisfying it. But you see this way, while even if we adopt this way of satisfying it, okay, if we do, that still leaves the values of the coupling integers for every value of alpha undetermined. This thing would be t invariant for every choice of integers, for let's say 5 for alpha and alpha bar equals 1, 27 for alpha and alpha bar equals 2, and so on. Okay? All those integers are completely undetermined. So even if we adopt this way, which I emphasize is not the only way, we make this ansatz to try to satisfy t invariance, that leaves the numbers in undetermined. So it's not enough. Of course, always the more non-trivial part of modular invariance comes from the tau transformations. So we are now going to try to study the implications of invariance under S transformations. Okay? Excellent. Is this already? I see. Wonder why this lecture room is so much worse than every other in the institute. Okay, excellent. To understand how to try to study invariance under tau goes to -1 by tau, we can't get away with the kind of cheap tricks we've been getting away with, looking at general structure. We need to dive deep in and look at a detailed formula for the character. Now, this formula that I'm going to write down such a formula. The formula that I've got, I can't remember if we wrote it down last semester, but we certainly discussed the straight structure that directly leads to this formula. Okay, so I'm going to write it down and then we will talk about it. Okay, so let me write it down. Okay. I define the quantity. Okay. There are various definitions we have to keep, this is technical, I'm sorry, but okay. Fine. Remember that our theory was defined by P and P prime, and our operator was defined by R and S. Okay. Now, one linear combination of P, P prime, R and S will appear repeatedly in our formulas. So it's good to give it a name. Okay, so we define lambda Rs is equal to Rp minus Sp prime. Okay, Rp minus Sp prime. Okay, excellent. Then, of course, lambda R minus S is equal to Rp plus Sp. That, of course, is true. Now, the formula for these characters, the formula for these characters was given by an expression that looks like this. Chi Rs is equal to KRS minus KR minus S, where KR minus S, I'm going to tell you what it is. Okay, let me write. Remember, lambda is lambda Rs. Yes, and n we'd written down earlier in this lecture. N is equal to 2p p prime. Okay, so first, is every term in this expression clear? Okay, we have 1 over eta of tau. and then sum over all integers, and then you get q to some power, which goes, in some way. Okay. Now, what was this sum? Okay. If you put in, these values of Rs, and you work it out at n equals 1, or n equals 0, this lambda Rs by 2n is basically the scaling dimension of that operator, of the primary operator. HRS. Okay? So you start with q to the power HRS, and then you keep changing q by various integers. Yes, you keep changing q by various integers. These integers keep track of how far the null state is in a given representation, and then how far the null state is in that other thing. Okay, there is. Okay, do you see that this is always integer? Because when you let me let's just work that out. Let's look at this object. This is nn plus lambda rs divided by 2n, and this thing is did I write the square? Which is it squared by 2n? Sorry, the square is up here. Okay, let's look at this. Let's take this guy's square and subtract it from n equals 0. Okay, so we get n squared plus 2n n lambda rs. Okay, this divided by n, by 2n. And now is this n, p and p prime were relatively prime. Yeah, p and p prime. This is clearly an integer. Could be a half integer, but there's something I'm missing. N is 2pp prime. Perfect. Excellent. So n is 2pp prime, therefore that is also an integer. Okay, so the differences are integers. And when you, the way this is obtained, of course, is that these levels, these descent levels, are the levels of the null states of these representations. Okay? The fact that we had both KRS and minus K minus RS is that you get, because you get null states, and then you get null states for null states. So the null states, the first null state contributes with a negative, but then the null state for null state contributes with a positive because you subtracted too much. Is this clear? This 1 by eta is the fact that if there were no null states, you'd have 1 by eta. Okay, so the structure is clear, right? It's that little diagram that I drew, just obtained in terms of a formula. Okay, so this is the formula for the character. Now, what we are going to do is take this formula and modular transform it. But we will not be able to finish by the end of this lecture, so let's leave it here. So what we have to do is take this expression and replace tau goes to 1 by tau. Okay? Now, fine, you replace tau goes to 1 by tau, you get something. But you want to rewrite it in terms of similar quantities with tau equals tau, not tau equals 1 by tau. Can anyone think of a method we can use for this process? Can anyone think of a formula of mathematics that we often use for such things? Poisson resummation. Right? So maybe I'll just leave you with the idea and then we work out the details next class. You remember, right, that the basic formula of Poisson resummation is, when you make the right conventions of 2 pi's, if you've got a function f and you want to sum it over all integers, this is the same as summing its Fourier transform over all integers. And then depending on conventions, there are some 2 pi's around the place. Okay? So the sum of a function over integers, same as sum over its Fourier transforms. Now what we've got is a sum of a function over all integers. Yeah, this little n is our integer. So we'll use Poissonry summation. We'll turn it into the sum of its Fourier transform over all integers. Now, you see, by taking tau goes to 1 by tau, q had become, so q becomes e to the power 2 pi I by tau with a minus and then all this stuff. But now, you Fourier transform a Gaussian. That gives you back a Gaussian, except that the coefficient of that Gaussian gets inverted. So when you do the Fourier transform, tau will go to come on the top. And doing it carefully, we will get an expression for this k of minus 1 by tau in terms of k of taus. And we will use that to understand the modular transformation properties of this object under tau goes to minus 1 by tau. But we won't be able to finish, so let's do that next time. Okay, questions or comments? Nothing? Excellent, let's go.